Hey everybody! In this episode of Simple but Evil, I want to talk about integrals. Integrals are our friend, and, well, I guess this guy is more sad than evil. Integrals are our friend. Integrals is something that we, introduce in a calculus course, and then it continues to evolve in later calculus courses. In the U.S. system, we have a course that's typically called Calculus 1 in college, and in this one we talk about derivatives, we talk about an introduction to limits, and then we also do your basic integrals. These are your antiderivatives in effect, integrals that you can just read off if you knew what the derivative. If you differentiated the integral, you should get back the integrand. And then we do a little bit of u substitution in the Calculus 1 course, but then in the Calculus 2 course is really where integration takes off, right? That's where we have u substitution, we have integration by parts, we have trig integrals, and we have trig substitution, and we have partial fractions, and so on. You'll notice that for a calculus course, penmanship is not a requirement apparently. But what is a requirement in these calculus courses is to have a good handle on the algebra that's required, right? Our symbol manipulation, knowing what a quadratic is, knowing what knowing basically just how to manipulate our symbols and how to manipulate our equations. And then, this algebra course builds into a pre-calculus course, which really focuses, it introduces a number of new things. One of them is, your exponentials and logarithms. We also get our trig functions, right? And we also have a little bit of graphing with parabolas, and this happens in an algebra course as well. But in a pre-calculus course, we dig a little bit deeper and we try to understand, well, how do you draw cubics and quartics and so on and so forth. And then, of course, from the pre-calculus course, we'll get to our calculus course. Now, one of the things that I've found in teaching my calculus courses is that there are, gaps in knowledge in algebra, between algebra and calculus. And by the time students get to Calculus 2, those gaps really start to hurt them, and they've spent all this time going through all these courses, and they never even had a chance to go any further. And Calculus 2 really is the separator, whether or not you will be able to continue into an engineering program. A lot of the engineering degrees require calculus beyond Calculus 2. Because this stuff falls into differential equations and partial differential equations, and you end up using some of the techniques you learn here. So what I like to do when I teach a calculus course like this is I like to get my students. I like to close these gaps, right? I like to close these algebra, pre-calculus, and calculus 1 gaps, and I like to do that by staying within the Calculus 2 content. So I don't so I'm still teaching this content, but at the same time I'm closing gaps. So first thing, so these are simple integrals. This is why I call it simple but evil. They're simple integrals that really should get our students thinking. Take a look at these three that I'm about to write, and I will explain why. What happens when we ask questions like this. So integral of 3 dx. Most students should be able to get this right, but there are enough students who balk at the 3 as an integrand. They don't really know what to do. This is our first check to see if some of the Calculus 1 stuff is retained. The next problem, of course, has an integrand of e. This is different from having an integrand of 3 in the sense that students, for whatever reason, still haven't processed or mentally accepted that e is a number. It's always e comes to them in association with e to the x. So they understand e more functionally than they do than they can see it just as a number, right? And in fact, they view e to the x materially differently than 2 to the x or 3 to the x. So, and if you ask them, where does e to the x fall if you had to graph this guy for x bigger than 0? would e to the x be less than 2 to the x? Would it be bigger than 3 to the x? Would it be between 2 to the x and 3 to the x? Many students just don't know. And next, we've got pi dx. Integrating pi is like this funny number. The students have seen it, since probably like the 3rd grade or 4th grade, but still have no idea what to do with it, especially when it shows up in a calculus course and it's not associated with a trig function. It's not associated with geometry. It's just there, sitting as an integral of pi dx. So I encourage, other instructors, and I encourage myself, of course, to ask these questions. This is a good way to just sort of show ourselves, hey, do our students really know what they're doing with integrals, or are they just mimicking steps? After you get through this round, right? So this is the first round. Here's the second round of questions with integrals. It's now hitting them on the forms that they have come to recognize. The integral of e to the pi is, a lot of students get this problem wrong just because it has the e, it has the exponent, it has pi in it, and what students are trying to remember is integral of x to the n dx, and when they try to integrate this guy, they've been taught over and over, well, this is just x to the n plus 1 over n plus 1 plus constant whenever, n is not equal to -1. -1. Like I said, penmanship is not a requirement here. So integral of e to the pi, I'll get wacky answers like this. I'll get answers like e to the pi plus 1 over pi plus 1. And this tells me that something has gone wrong. They're looking at the wrong form. Of course, this is not correct. The answer here is just e to the pi times x plus constant. So ask questions like this, right? E to the pi, pi to the e, so on and so forth. The third set of questions in this world of these simple integrals is the integral of e times x dx. Now, many students, if you ask them the integral of 2x dx, they should be able to get this right? Once you've gone past your basic integrals, they can answer this question correctly. But ask them the integral of e times x, now they're confused. Because you have an e, you have a times x, they've only ever seen integrals involving e to the x, so they don't know what to do. Again, this is a good sanity check for you as an instructor to say, wait, do my students actually understand e? Do they understand an integral? Do they understand what a constant is? And that bit. And you want to try to relate it, integral of e times x, and show them, well, how is this any different than the integral of 2 times x? Similarly, you can do this with integral of pi times x, right? The next set of questions, right, involve x raised to some power, because now we're going to start hitting them again with this power rule that they know. But it's now x raised to e, or x raised to negative e, or x raised to pi, or x raised to pi plus e. And you can see where I'm going with this. You can mix and match the e's and the pi's and the exponents using the basis x. They should still be able to use this power rule, but the very presence of this e sitting in an exponent, it now messes with their ideas, because all they remember is integral of e to the x is e to the x plus constant. So now integral of x to the e, well, that looks so close to the integrals that they know that it's hard for them to see that this is no different than the power rule problems that they've been doing, and they've been doing correctly. Okay, so these are my first set of simple but evil problems. Now the next set really focuses on the derivative of ln, ln of f of x, right? So the derivative of ln of f of x, this is where students seem to have a little bit of difficulty, because while they learn in Calculus 1 that this guy's derivative is f prime of x over f of x, they also forget it in Calculus 1. So by the time they get to Calculus 2, an integral of the sort, and this is probably a little bit on the evil side, but it's worth asking, right? The integral of 2x times ln of x squared plus 1 over x squared plus 1 looks like a completely difficult problem. This looks like a horror show, right? You have an ln, an x squared plus 1, you have an x squared plus 1 in the denominator, you have 2x, you don't know how it's going to work out, because all they know, right? Here's what they think. They think that that 1 over f of x is the derivative of ln of f of x, which is incorrect. So now they see this and it doesn't make sense. Some of them will make a good u substitution, right? They'll try with x squared plus 1 for u, and they'll be able to resolve this and show that it's ln of u over u. But that's still, then they have to now make a second u substitution, and some students are not comfortable with that. So this is a good way to remind them that, hey, derivatives of natural logs involve, derivatives of this form, f prime over f. All right, so there's your natural logs, right? Now, third set of questions, gets us to our trig stuff. Now, our trig stuff is fun because students don't understand how function compositions, especially for these trig functions, work. So there's a difference between the integral of half sine of x versus the integral of sine of sine of 1/2 x dx, right? These are two different problems, but students can't understand why they're two different problems. So I encourage asking this question and at least having the dialogue. Well, what is the difference between these two? And the problem, of course, is that they don't understand what the argument of sine is. Because even when they speak it, they say integral of sine is cosine. That's how they say it. And lost in all of this is the argument, right? It's the integral of sine of x dx is cosine of x plus constant. But they don't say it that way. They engage in a short form version of this, which leads to this protracted confusion about how these integrals should work. Now, sticking with our trig functions, and I'll give myself some more room on the other side, we have our trig substitution problems, right? Now, these involve our students to know our trig identities, right? We've got sine squared of x plus cosine squared of x equals 1. And unfortunately, students end up memorizing the second equality as well, but there's no need to memorize it because we can get to it from the first equality. So this is simply dividing by cosine squared. And then, of course, once they have tan squared plus 1 equals secant squared, they should be able to do the symbol manipulation or the algebraic manipulation to get our other identity, that's secant squared x minus 1 is equal to tangent squared x minus 1. But unfortunately, students try to memorize all three of these, and this leads to a little bit of cognitive overload. So there's your first problem here, right? It's to make sure that students aren't memorizing these identities. It's that if they want to commit to memory, sine squared plus cosine squared is equal to 1, and you see I'm even saying it in the short form, sine squared plus cosine squared. But if they want to memorize the first one, that's okay. But the second and third identities should just be derived always, and then eventually it'll just become part of memory rather than something that's been committed to memory by force. So once they've gotten over this, what I like to do is I like to and when I'm in a trig substitution section, once I've explained how trig substitution works and they've gotten a handle on a bunch of problems involving trig substitutions, I like to ask them a simple question like this. This is the integral of x squared plus 1. Now, they've become overconditioned with solving problems like integral of square root of x squared plus 1 dx, where, of course, maybe not exactly this problem, this is a little bit goofier, but sure, in a problem like this, you do want to integrate via trig substitution. You want to make the substitution x equals tangent of theta, and even problems like this, 1 over square root of x squared plus 1 dx, right? Both of these require a trig substitution of x equals tan theta. So what students end up recognizing is, they recognize this form of x squared plus 1. And so when asking a question like, hey, the integral of just plain old x squared plus 1, they will, when they're in the trig substitution section, default to trying to integrate this with a substitution of x equals tangent of theta. Now, this will work, but why do we want to go down this route when we can simply integrate this as x cubed over 3 plus x plus constant, right? This is a direct integration from our power rule for polynomials. So I like asking this question as a good starter to make sure that, hey, please remember that just because we're in trig substitution land doesn't mean that everything requires a trig substitution. It's important, I think, to make sure that students see a more cohesive view of integration techniques rather than, now we will use trig substitution, now we will use partial fractions. So sticking with this, I like to also toss in problems that don't require any type of trig substitution, even though it looks like it does. This guy is a U substitution, and a problem like this sometimes doesn't make it into the U substitution section for whatever reason. But our U substitution, well, one of them could just be U equals x squared plus 1. Now we know that du is equal to 2x dx, but of course we have an x cubed up here, but we have a way of getting an x cubed out of this, which is u minus 1 is equal to x squared. So this integrand really just becomes, right, what does it become? It just becomes u minus 1, that's my x squared, divided by 2, right? That gets me my x dx, which is now basically my x cubed. And then all of this again divided by the square root of u du. So then if I wanted to clean this up a little bit, I can clean this up by writing this as u minus 1 over 2 square root of u du. So, a lot of students tend to have a difficulty with doing just this integral because, for whatever reason, they can't necessarily see that you should rewrite this as two separate integrals. So it becomes a continued process in making sure that we can take multiple steps of integration and solve these problems. This is something I think that lacks in some of the way that we end up teaching calculus. Not all of us. I think a lot of us do this. Good justice, serve calculus well here by making students go through problems like this. But I think it just doesn't happen enough because I see it in my calculus students, right? I see these failures where, they can get maybe they'll see this U substitution, but that doesn't happen often. They need to see it at least once to have the idea. Then once they have the idea, it becomes something that they can add to their repertoire. And in the same way that, as teachers, once we see that we can give a problem in a certain way, we add it to our repertoire of problems to give. Now, the final problem I want to give involving trig substitutions is really testing their preference for form. I like to ask this problem because it looks very close to the integral of 1 over the square root of x squared plus 1, right? But they can't make the substitution of x equals tangent because of our negative sign. And this integral of 1 over the square root of negative x squared plus 1 is different from the integral of 1 over the square root of x squared plus 1. And what students end up doing is that they end up seeing this form too often, right? This x squared plus 1 form too often, that they want to, they force an x equals tangent substitution, but the problem is they haven't rewritten this in a form that they can recognize, which is 1 over the square root of 1 minus x squared. If you ask students, these two questions, maybe a few questions apart from each other, you may be surprised as to how many students get 1 over the square root of 1 minus x squared correct, or that integral correct, but are unable to do the equivalent one, where all I've done is just change the order of 1 minus x squared and rewritten it as negative x squared plus 1. So this is the whole idea behind simple but evil. We don't actually want to be evil. What we want to do is we want to try to give them problems that they have seen, but we're twisting them a little bit so that we break them out of the mold of the patterns, right? They've seen a lot of different patterns. They've seen patterns like, x to the n, the integral of x to the n, but they don't see questions like integral of x to the e, because they only see e in the context of e to the x. So while it's good to have, patterns, you can understand mathematics a little bit better. You can maybe even understand life a little bit better if you understand the patterns that you see. But if you don't see enough of these patterns, you get confused when you see something a little bit different from a standard form. And of course, part of this confusion is because we don't understand, this standard form well enough. We don't understand what this n is. N almost always happens to be an integer in this integral of x to the n. But why not ask a question like integral of x to the 2.7 plus square root of 3 dx, right? You'll be surprised that a question like this also trips up students. So this is the whole idea. This is the whole point of Simple But Evil. I will have more of these videos coming out over time. In the meanwhile, I hope you enjoyed this one. If you like it, give it a like, give it a comment, give it a share, subscribe to the channel. And also you can check out the blog here at the top right, where I talk about this particular topic a little bit more in detail, and it has links to the other Simple But Evil series that will be coming out as well. In the meanwhile, thank you, enjoy, see you next time.